Yes, hello everybody and welcome to Fizix, Trix. Don't worry, I'm going to sort that title out in a minute. I really am. Not my choice to name. That's what happens when you let the university marketing department get involved with these things. No, I'm nowhere near down enough to keep going with that. So, we should probably start by introducing ourselves. We're all PhD students here at the university. My name's Dave. We also have Rob, over there, Maria, and the beautiful Samantha. Sorry, Faris. Faris, everybody, yeah. Radio 4 listeners might get it. There's Radio 4 listener right there. Okay, so, first and foremost, the first thing I'm going to do is change that spelling. That's not how you spell physics, that's how you spell physics. Spell with P-H-Y, not F. Okay, so that's how you spell physics. The second thing I'm going to do, I'm going to change the second bit. It's not going to be called Trix anymore. And please let me finish this because half of you will probably try to stampede the doors. It's going to be a lesson. Okay? I'm calling it a lesson. Oh, this is good. Last show when I did this, I brought a lesson and everyone went, ooh. Okay? I'm calling it a lesson simply because you're all going to learn something. Absolutely every single one of you can learn something. Even Dr. Safin down the front here. Now, he works in gravity as far as I'm aware. He teaches the gravity module on the course. Very, very clever guy. He's going to learn something today. Although in his case, it probably won't be physics. It'll just be that watching me risk life and limb for the sake of science makes great entertainment. Also, we've got a very special guest here today. My mum's here. Hi, Mum. Hi, I was only kidding about the risking life and limb. So you've learned something already. Apparently, scientists have knowledge. Okay. So before I tell you what the theme of our show, and there is a theme today, I want to explain a little bit about why we're doing the show. Why I'm making a lesson, why I'm going to tell you something, why I'm going to try to teach you something. And it's because, as a scientist, and I strongly believe this is why I do science, the more you know about the world, the more beautiful it becomes. And that sounds like a strange word, the more you know about it, the more beautiful it is. If you know what's going on, you know why things work, it becomes so much more interesting, so much more beautiful, even very mundane things. I'm the sort of guy, I'll walk along with my cup of coffee and I'll notice there's an interesting pattern in the waves as I walk along, and then I'll walk straight to the door and spill it all over myself. But then I'll get very interested about the way that he spreads around my t-shirt, nice little diffusion patterns going on my t-shirt, this sort of thing. The world becomes more beautiful, and hopefully today I'll teach you a little bit about something, and you'll be able to go away and you'll look at the world in a slightly different way, and it'll be a more beautiful world for you. That's a very, high stated goal. Worst comes to worst, I'm going to buy some stuff up, so no, it's not too bad. I should also start with an apology as well. So on our flyer, we promised you cannon, explosions, levitation, and bananas, I believe. Yeah. Unfortunately, before the show, we gave the bananas to Faris to look after. Yeah. Faris hadn't had any lunch, and now the bananas are missing, Faris's words. So there'll be no bananas, I'm afraid. I'm sorry.
You have the gherkin.
I feel like I'm letting you down.
You have the gherkin.
Pardon?
You have the gherkin.
The gherkins, oh no, unfortunately again, the gherkins aren't part of the show. That's what happens again when the university gets involved and don't ask me what I'm doing before they write something. It's not that impressive anyway, they just go over it. You can find it on YouTube. Not much more impressive stuff than that. So yeah. Right, so what's the topic of our show going to be? Don't move, probably a bit too, no, I'm not going to bring that up. So we're going to talk about something that's all around you. You probably never think about it. Any guesses?
Air.
Oh, you shouted out. So let's just theatre, hand up, wait for me to ask you. That's a bit here. No, you're right, though, you're right. I need to make that a bit harder because the last group got it as well, first time. Air. Okay, so you never think about it, most of you, I imagine. Just around you. But I'm going to teach you stuff about it. I'm going to show you some really neat stuff you can do if you mess around with it. And I'm going to show you can actually start to learn a lot about all the different things in the world, just by considering what happens when you mess around a little bit with air. So the first thing you should know about air is that it's made of something. I imagine a lot of you know that air is not just nothing, but maybe some of you haven't really thought about that. You just think of air as being the space around you. There's actually no stuff in air. Okay? So this is our physicist's picture of what air looks like. There's these little snooker balls bouncing around, and each of those are molecules, these very, very small things, the smallest things they can be really, bouncing around, and that's what air looks like to us. Now air's actually not all made of the same thing. There's a few different things in it. There might be nitrogen, that's nitrogen there, but that's about 70% of the air. Okay? There's oxygen, probably about 20%. Oxygen because it explodes, which is why the university won't actually play with liquid oxygen. And then there's some other stuff in the air, which is this little ball. The rest of it's this other stuff, so that might be stuff like carbon dioxide, sort of trace gases, that sort of thing. That's not really that interesting for as far as we're concerned. So air's made of something. Now how can I show you that air made of something? Well, very simple question. It starts with a boat. If I had a hammer and a feather, and I held them both out, and I dropped them at the same time, which would hit the ground first? Everyone looks the hammer. Okay, hands up for hammer. Okay, interesting. Dr. Suffin's kept his hand down. What about the feather? A few hands up for the feather. In fact, Dr. Suffin's kept his hand down for that as well. Okay, well let's try it out. Okay, so I've got a tube here. Now at the moment this tube is full of air. It's also got a little hammer and a little feather. Can you see them in there for me? A little hammer and a little feather in the bottom there? You see them? Okay. I'll come back to you, don't worry. Yeah, it's a little feather, a little hammer. Okay? So if I turn this upside down, see the hammer hit the ground first and then the feather. I'll bring it over here so the guys can see it. More gesticulating while we come this way. Okay, so you guys can see it as well. The hammer and the feather. See how much longer the feather takes to hit the ground. So most of you were right, okay? The hammer hits the ground first. Of course it does, that's pretty intuitive. The reason it does that, and the reason it doesn't go the same, is actually because of the air. It's not because the hammer's heavier, it's because of the air. So if I give this to Faris and Maria, they're now going to suck all the air out of that. They're going to get rid of all the air. And it's going to, what's going to happen is it's going to change. Actually, by doing this, we're going to learn something about gravity. Okay? But what we're going to learn is that when things are falling under gravity, the rate at which they accelerate in a vacuum is the same. Okay? Things under gravity fall at the same speed. So this time, when the air's gone, and you can see Faris is sucking it out now, he turns it around, you'll be able to see the needle going down. Okay, we're pumping it down to roughly sort of the vacuum of space. So it's now like space inside that tube, or nearly soon. This time when I turn it over, they should fall at exactly the same speed. They should hit the ground at exactly the same time. Okay? Because that's what the theory of gravity says they should do. Okay? We're now under vacuum. Cool. Thank you, folks. Okay, so this time, go a bit further up. There you go. See the feather hit the ground there? Oh, didn't that time. See, you hit the ground at the same time. Right, I'll come over there again as well. Right. See, you hit the ground at the same time again? And just by removing the air, we've learned something about gravity. Ow! Awesome, biggest laugh I've got all day. Okay, if I let the air back in, you'll see again the feather slows down, okay? So there we go. So, that was just using the Edson's route, it's normal air pressure, okay? So the air that's always around you. Now you never notice that, you never feel it pressing down on you, but it's quite powerful. You've just seen what effect it can have. Okay? It's actually so powerful, we're going to use it, hopefully, to send a little foam ball, what we're providing with now, a little foam ball to a Coke can. There you go. You want to catch that? That's pretty light, isn't it? Do you think we can fire that to a can just using air? No, you don't. He's probably right. He's probably right. Okay. Yeah, this experiment is somewhat temperamental. We tried it this morning and it didn't work 3 times. But hopefully it should go through as we can. So what Rob's going to do, he's going to load that ball in there. This is our vacuum cannon. We load the ball in there, all the way down, and he's then going to seal the ends up with parcel tape. So it's one end sealed up already. He's taking this all the way down there. God knows how many times he's done this experiment in practice. Okay, so we're going to seal the end with the parcel tape. And then once that happens, you'll have this, okay? So both ends of the tube will be sealed, and there'll be loads of air in the tube. We're then going to suck all that air out. So it'll be in the vacuum again. Like this. And at this point, you should see the tape at the end. You probably won't be able to see it from where you are. The tape at the end will follow it's being sucked in. It's on the vacuum. And then that's when the fun starts. The Rob's going to take a knife, he's going to jab the end of it, and all the air is going to come rushing back in. Because there's all this air outside and there's no air inside, so it wants to rush back in. As it does that, because it's only coming from one end, it's going to push the ping pong ball. Now that's going to accelerate the ping pong ball quite fast. The ping pong ball is going to want to go. And also, because there's no air in front of it, it's going to go really, really fast. You've just seen what effect air has on things falling and accelerating. So the ping pong ball is going to go really, really fast, pop out the other end, and absolutely certainly 100% do something to the can, maybe. Okay? So yeah, I'll put the backstop in because if it does go through the can, we don't want it to kill Paul. The other thing I should point out is that when this goes off, it's quite loud. Probably the loudest thing we've got today. So when one turns the pump on, you'll see me, Marie and Faris, we're all going to go like this. Okay? And when you do that, hands over your ears. Not in your ears, you'll push your brain out. Over your ears. Alright? Okay, so pump's on, hand in your ears. Are you ready? Yeah, I didn't work. All that you got tuned. Okay, we'll give them one more chance to get it right done. Okay, so the next useful thing we're going to talk about air, the next thing we're going to learn about air, is quite a good one. You're going to learn why you can hear it. Because air is useful for a lot of things. Obviously breathing is a good one. But hands up who's seen Alien? Slightly older generation here, who's seen Alien? Yeah, okay, cool. Who can tell me what the tagline is? Space, no one can hear you scream. And that's because there's no air. So what we need to do is we need to tell you a little bit about sound for you to understand why that is. So sound is what we call a pressure wave. And essentially all this means is you get these little compressions, so little concentrations of air, or whatever sound's moving through it, in this case the air, little concentrations of air moving along. And that's what we hear as sound. It doesn't have to be through air. Like I say, if I knock on this bench, that sound travels through the bench as well. Compression's moving through the bench. But that's all sound is. So here we can see. If you imagine this is our sound wave here. This is our sound travelling through the air. This is just normal air here. This is compressions of air. Little compressions of air moving around. And if Faris comes over here, and we get the slinky, you'll see how they move. So if Faris makes a noise now, you guys can see the compressions moving through the air. So that's what sound works. Sound is just compressions of air. Now there's another property of waves I need to tell you about to show you what I'm going to show you next. This is a very useful property, a very useful thing that waves do. And it's called superposition. Or essentially, waves add together. You can add waves together. It's a key thing for that. So if you have two waves like this, and you notice there's little peaks in the wave, there's little low bits in the wave, high bits and low bits. And if you take two waves, the high bit's the same, in the same space, you put them in the same space, they will add together, and you'll get a wave twice as big. So the high bits have the high bits, the low bits have the low bits, and you get bits twice as high and bits twice as low. On the other hand, if you take a wave where the high bits and low bits, two different waves matched up, so in this case the high bits matched up with the low bit, high bit with the low bit, high bit with the low bit. In that case, you add those two waves together, they cancel out, because the high bit adds with the low bit, and you get nothing. You just get nothing. This is a fundamental property of waves. Now what can we do in this that's interesting? Well, we can levitate things. We can levitate things just using air and just using sound. So sound and air we can use to levitate things. So this is our hypersonic levitator. Now we call it hypersonic because the sound we're going to use is hypersonic, which means you guys can't hear it. It's too high a frequency for you to be able to hear. If there are any dogs in here, they're about to go mental. Okay. Unfortunately, there are no dogs in here. So, Faris is going to turn this on. Okay. So what we have is, we have a speaker, which is this bit up here. If you look at the screen, that's the speaker up there. And we've got a little reflector down here. So the speaker makes a noise, these little compressions on the speaker, pressing down, they bounce off the reflector, going back up towards the speaker. Now at this point, there's still waves coming down from the speaker. So we've got sort of two waves in the same space. We've got the wave on its way down and the wave on its way up. Now we're very, very clever, and we make sure that the sound we put out has compressions at the right distance apart, and then we match that to the distance in between our speaker and our reflector. We can make those compressions, we can make those high points, those low points, we can make them line up. And low points will line up. So they'll add together. And we'll get what's called a standing wave. So we'll have areas that are very compressed, these add together in some place. You get some areas where there's a lot compressed there, and some areas where there's not. And what this means is, we can levitate things, we can stick things on these clouds are there, as far as the computers now. If you look at the screen, you've got some little polystyrene beads, and if you're very, very careful, you put them in there, nearly. And there you go. And actually, if it carries on, so you'll be able to see that there's more than one strong one there, there's more than one bit there. And you'll be able to sit a little polystyrene board on each little compression there at the top. That's pretty cool, isn't it? There you go. Just using a bit of air and a bit of sound, you managed to levitate things. I'm glad that's worked because that's a little side project I've had going, and I sort of built it because I thought it looked cool and I had no idea what to do with it. My supervisor thought she was doing some research with it, but it's good for this. So I've just told you that sound is these compressions of air, and as you see, it's actually powerful enough to beat gravity. Compressions of air, pretty powerful. Gravity's pretty strong. Maybe not compared to other forces, it's pretty strong. And so this compression there is strong enough to stop it. So why? Come on, yeah. Why can't you feel me talking? When I talk to you, that's just sound. So when I'm talking to you, why don't you get knocked back by these compressions of air when I'm talking to you? Any ideas? Hands straight up. You said it's not very strong, which is the right answer. Can I handle there as well, go on then?
Because of gravity.
Because of gravity? Not really, it's very simply. Very simply, your voice spreads out, it's not that strong. It's kind of a trick question because you can feel it, because you can hear it. That's what the ear's doing, it's feeling the sound. That's what the ear's really, really doing. If you get a chance, I do encourage you to go look at the way the ear actually allows you to get it. Because there are these tiny, tiny fluctuations in the air. And your ear can pick them up, amplify them so they're much, much bigger, send them to your brain, and then interpret that as sound. So you have to listen to me, get to hear me speaking. Okay? So there you go, that's what it is. You could if your skin was much more sensitive. So what would we do if we wanted you to feel air moving along? If we wanted to make a compression of air move through the air, when you look back up there, we wanted it to have some power. How could we make it more stable so it would reach you in one piece rather than going away? Well, we've got a hand up. You got any ideas?
Make the sound lower.
Make the sound lower. That's actually not a bad idea. Probably not enough, but that's actually not a bad idea. Oh, how about this? Right. Do that. Try that me on. Yeah. Okay. So do you want to notice what you did there? Throw it like a frisbee. That's the key thing. You don't throw frisbees like that, do you? It don't work very well. You spin it. Like that. It'll work a lot better. And that's on something we call the conservation of angular momentum. But very simply, spinning things normally want to carry on spinning. I can hear Dr. Saffron wincing. Spinning things normally want to carry on spinning. That's why bicycles work. Because your wheels spin and want to carry on spinning, so that's why you're actually quite stable, even though when you look at them, they're pretty ridiculous bits of kit. So we need to spin the air in some way. So we're going to have a little look at how we do that, which means we're going to need volunteers. Okay. Well done, what's your name? James. Cool. Ali. stand here for you guys. Right? Now, Jeremy, first, I want you to stand here. Right there. I want you to blow those cups over. Come on. Come on. No, the best you can do. No, it's alright, you are quite small. Let me do that. Ha! Ha! No. Not bad. Okay. Don't worry, it could just be because you're quite small. Let this bigger guy go. Go on. He's just embarrassing himself. Oh, you can have that. Okay. Obviously, Forrest is cheating a little bit there. He's not going over himself. He's using a vortex can. A vortex can, very fancy sounding. But all he's done is he's spun the air. So he's taken the air. He's forced the load of the air out of this thing as he lets this thing go forward, it forces all the air out. The air comes flying out here, out the circular hole, hits the air around it, and starts to slow down around the edges. There's all this fast moving air going into all this slow moving air. He starts to slow it down. And when he does that, he starts to go around back on himself like this. Now you recognise these patterns, these little eddies. You might see them in a river. The river splits around the rock, you can see these sorts of things going around. So they're quite common patterns. And eventually it goes right back round on itself and forms these rings. If we put a bit of smoke in the box, we can show you these rings and talk about it too. So now the smoke's not necessary for that to work. What the smoke does is let you see the rings. And what's actually quite interesting is, it's not that there's just this moving sort of like that. We're actually carrying the air with it. It's carrying the smoke with it. So we're actually carrying a packet of air through other air just by spinning it. Rob's going to show this now with our smell pan. You know, you've been into all the department stores and you're sort of walking along and all of a sudden somebody jumps out and says, "Would you like to try the new Calvin Klein?" Sprays you in the eyes and then you punch him and get done for the salt. Whatever you do, don't let me find out about this. Okay, so you spray a load of deodorant in there. Can you smell it? You people? I can't. You smell a short from there, loads of quantities. So yeah, carrying the smell, carrying the deodorant through the air. So yeah, if department stores get hold of that, they're absolute nightmare. What's next? Oh yeah. There we go. So what does the temperature, what does the amount of heat the air have, what does that do to gases? Anyone know? If we heat air up, what happens to it? Anybody? Come on, there's loads here. Got a hand up? It moves faster. Yeah, very good. So the atoms move faster. What does this do to the size of the air? If you've got a certain amount of air and you heat it up, what happens to it? It gets bigger, it expands. Right? So what we have here, to talk about the solid, is this is the gas, okay? All these little atoms knocking out there, this is the gas. Now at the moment it's quite cold. There's all the atoms flying around here, it's quite cold. Rob's now going to heat it up. There we go, he heats it up, and it gets bigger. There you go. Under the same pressure, you heat the gas up, it's going to expand. Now we can have some fun with that. And if we're going to start having fun with things and messing around with heat and temperature, it needs some liquid air. And this is where it starts to get fun. Unfortunately, it's not really liquid air, because like I say, liquid air contains liquid oxygen. And when I mentioned to the school that I wanted to mess around with liquid oxygen, the health and safety guy got a bit annoyed with me because it's fairly explosive. So we're just going to... Yeah, but he's not here. So, now we're just going to use some liquid nitrogen, because they're mostly nitrogen. So here we go. We need some nitrogen. Right. when you said that you'd lost the bananas. In fact, what you're doing is, you've put the banana in the liquid nitrogen. Right. I'm going to give you guys a choice at this point. If you want me to smash the banana, and then you're going to shout out banana. If you want me to hit Faris, shout out Faris. Okay? On 3. 1, 2, 3. One more time. You know, if I hit the banana, that I heard. No, it's not really got anything to do there, but it's like an unwritten rule that if you've got liquid nitrogen, you're going to have to smash a banana. Okay, so this might fly into the crowd. Don't pick them up, just knock them on the floor. There we go, that's what inside a banana looks like. Sorry. Just hold it for the smell of the banana, just when that melts. Right, there we go. Okay, so, what I do with my little thing? There we go. So liquid nitrogen. Probably need to know a little bit about it first. You all know it's cold, yeah? Everyone's aware that liquid nitrogen is pretty cold. But just how cold is it? Well, if we put our scale up there, and you can see on the scale here, so this is how hot you are. 37 degrees, that's how hot you all are. Hottest day last summer. In here it's probably about 22, 23 degrees in here right now. A bit colder outside. Now we're down to our fridge, so that's pretty cold. That's 5 degrees above 0. So you normally think that's pretty cold. This was the coldest day we had this winter, a bit of snow around. And then it's your freezer here, about minus 18 degrees. So most of you think your freezer is pretty cold. Okay? Show them how cold liquid nitrogen is. Okay? So there's your coldest day, minus 18, and here's liquid nitrogen all the way down here, minus 200 degrees. So it's really, really quite cold. And you've just seen what it does to bananas, so it is quite dangerous. So whatever happens, you shouldn't stick your hands in it. You can. Well, I can, you shouldn't. I'll get in trouble if you all go away and find some liquid nitrogen and say, oh, the nice one at Nottingham University said you could do this, and stick your hand in it. Anyone have any idea why you can do that? All hands at the back. Go on then, back corner. It forms a kind of bubble wrap, very good. Do you know what it's called? It's called the leading frost effect, which I would have been amazed if you did know, to be honest. So what happens is, I've just shown you how warm I was. I was sort of all the way up here, sort of 37 degrees. And nitrogen's all the way down here, minus 200. So when I put my hand in the nitrogen, my hand's so hot compared to the nitrogen, that it immediately boils all over the nitrogen. It turns it from a liquid into a gas. And all that gas then, all that nitrogen gas, forms, like he said, a little glove around my hand. It forms this nice protective barrier around my hand. And because heat doesn't travel very well through gases, because there's not much stuff there really compared to, say, a liquid or a solid, my hand's okay, it's protected, it's insulated. The heat can't get from my hand into nitrogen, so I don't get burned. However, if I leave it in there too long, that cloud will collapse, then the heat will leave my hand, and then I'll get horribly burned. Which might be fun for you guys to see, but I'm not going to do. If I'm very clever though, if I keep it moving around, I can actually hold it in my hand. You can actually hold liquid nitrogen in your hand, which is quite cool. If I was a really stupid Russian guy who used to work here and then went on to win a Nobel Prize, I'd drink it, but again, not doing that. You should stand back and pour it over and sort of, yeah, win a Nobel Prize. But we're not allowed to do that anymore. So anyway, very cold. What's it have to do with gases? I've also probably noticed loads. Okay. So I've told you, when you heat gases up, they expand, and when you cool them down, they contract. So this is a neat little party trick I'm going to do for you now. What you do is you get yourself some liquid nitrogen. I guess you can get it from Sainsbury's. They don't let me outside the physics department, so I don't know where you get it from. You get your liquid nitrogen from Sainsbury's, and you bet your mates a tenner that you can blow up the balloon from the outside. Okay? You get your balloon. Stick it in liquid nitrogen, and as it cools down, the air inside the balloon gets smaller. Okay? So there you go. There's still the same amount of air in the balloon, it's just smaller because it's colder. So if we blow it up and warm it up, thing we should tell you. So if you've got liquid nitrogen, it takes up a certain amount of space. Say you have a litre of liquid nitrogen. When that turns into a gas, it expands a lot. So as you heat a gas up, it expands a bit as itself. If it goes from a liquid to a gas, it expands a lot. In nitrogen's case, it actually expands 700 times. 1 litre of liquid nitrogen will turn into 700 litres of gas. So, we've got a little ping pong ball here, and there's some holes in it. If we fill it up with liquid nitrogen, we're going to get lots of liquid nitrogen in there. We're going to take it out. When we take it out, the nitrogen should hopefully heat up, come flying out the sides, and we'll have a little jet engine. Hopefully. It was a bit temperamental last time. Okay. Come on, you can do it. You can do it. Start to spin. Okay, so that's just the nitrogen inside it, turning into a gas and expanding and coming flying out of those holes. It turns into a little jet engine. So that's actually worked alright. You can kind of see that on the camera. We can do it, we can show the same thing a little bit more obviously. There you go, get that. Put some nitrogen in here. Some indicating. Okay. And we cover it up. See, so the nitrogen inside there is boiling, expanding rapidly, and it starts blowing the balloon up. We can do it a slightly different way. One nitrogen there for this. Okay. If we push that in, and fix the volume so we don't let it expand into the balloon, and then we're pushing the plug on. And we can. I really want to try this thing. Okay, well, I'll really go for them. Just get me standing knife in case I need to avoid this. Right, so. Okay. Okay, so moving on to our last little topic here. What else is there in the air? I've told you there's nitrogen, there's oxygen, a few other things. Who else can tell me something else that's in the air? Hand up at the back there. I'm sorry, I didn't hear that. A trace of methane, there might be, yeah. Something that's not a gas. Go on then, down the front. Alright, now. Go on then. Sun? Sunlight in the air, folks, is going through. Dust? Yeah, these are all good answers, not what I'm looking for, but this is better. I hate it when you get the questions first time. Water vapour, there we go. Give a round of applause. So there we go. There's water in the air. Now you know this because there's clouds in the air. Frequently there's lots of clouds. Okay, so clouds are just water vapour. I don't know how clouds are made.
By rivers.
By?
Rivers.
By rivers. What do you mean by rivers? I don't know what a river is, but...
And it goes through it down the... Like it's hills and goes down...
Yeah, got it. Condensation. Okay, you got it. Yeah, you got the word I'm looking for. Condensation. Okay, so you get all this water vapour in the air, and what happens in clouds is they get very, very high, and the air cools down, and all this water vapour starts to condense, which means it sort of collects. It collects into these little droplets. And then these little droplets scatter a load of light in there, and that's why clouds are white. And then you see clouds. So they're just little droplets of water high up in the air. So that's how nature makes a cloud. Condensation, solar gravity, cloud. What happens if we want to make a cloud? Same thing. All we've got to do is get some water vapour very, very cold. And that's going to make a cloud. Okay? So we're going to start off on demonstrating. Excuse me, I need to get changed. Okay, so just amuse yourselves for a minute. Make our cloud, like I said, we need to get some air. Well, we need to smell the bottle of water, it's very, very cold. Now we've just been playing with something cold, you saw I had a little bit of nitrogen there. There was a bit in there, maybe a litre, nothing now. Okay, so here, I've got 25 litres of nitrogen. Alright, that's a bit. Okay. Right. Now, some of you might be thinking, he's just going to vaporise 25 litres of nitrogen, and he's just told us that what happens, it expands 700 times. And it'll fill the room with nitrogen, we won't be able to breathe. Don't worry, we've calculated that almost certainly won't happen. No, it won't, and genuinely we have to do the calculation. We also have these are little oxygen depletion meters. So if the oxygen gets too low, these will start beeping, and you guys will probably be fine with half a kilo over, and then we'll be happy. Alright, we've also opened the doors, we should be just fine.
Okay. So, a lot of liquid nitrogen, what full of hot water. Okay, you guys ready to make the cloud? Yeah. Alright then.
So, before I leave you, I'm going to finish with a quote. It's from one of my favourite physicists, and he actually allows to have favourite physicists. Okay, a guy called Richard Feynman. The quote is very simple. Our imagination is stretched to the utmost, not as in fiction to imagine things which are not being there, but just to comprehend those things that are. And this brings me back to where I started. What I wanted to state is, what I want you to take away from here. The world is a more beautiful place when you start to understand it. And I hope in some way I've changed the way you look at the world a little bit today with regards to that. I hope I've encouraged you to go away and learn a little bit more about the world, because it makes it a more beautiful place. And that's why science is so brilliant. Okay? Thank you very much for listening.